What are the pKa values you said you did memorize?
What are the pKa values to memorize? Basically, on the list, so I gave you the list on eCampus of pKa values, and pretty much all of the ones except the carbonyl compounds, I believe. Of course, I don't have them here. So the halogen acids, I don't really care that you know those specifically. Know these oxygen acids, know the thiol, know the nitrogens, and the hydrocarbons. Okay, now we're not going to use pKa's exclusively on the exam, but there might be a question or two that just asks you about specific values.
Can you repeat that list, please?
Okay, so oxygen acids, nitrogen compounds, hydrocarbons. ONC. Yes?
So if you have a question that you could figure out using pKa values, can you figure it out using other ways of analyzing acid and base strength?
Yes, so the thing is there will be one specifically like equilibrium problems that you could use pKa's and just find that the reaction falls to the side opposite the stronger acid, or you could use the trends and look at the base versus a conjugate base and find the one that's more stable, and the reaction lies to the side of the more stable base or conjugate base. Or you could use both ways and they should both give you the same answer. Yes?
Can we go over a couple more examples of like how to figure out which way the reaction lies?
Uh-huh. Yeah, so let's do a couple of those. All right, so we want to figure out which way the reaction lies. So let's try well, crap. Bear with me. Okay. Okay, so let's say you're given these two reactants, and maybe I'll have you do several things, and I'm highlighting the hydrogen that I want you to treat as acidic in the second molecule. Okay, so maybe I want you to first draw the product. Okay, well let's highlight our acid, which has the proton to donate, the base, which will take the proton. Okay, so you might be asked to draw reaction arrows. So always put your pencil down on the lone pair or electrons. We're representing that by the negative charge here. We're going to go over, form a bond to the hydrogen, and then I'll move these electrons from the bond onto the carbon as a lone pair. So we can draw the products. Okay, then maybe you want to label the conjugate acid and the conjugate base. So the conjugate acid is the species that has the new proton. And the conjugate base is the other species. Okay, now to predict the direction of the reaction, you could use pKa's. So on the acid, and you're only doing pKa's of the acid and conjugate acid. You can't do pKa's of a base. pKa of that acid is around 55. The pKa of this hydrogen next to the carbonyl is around 20. But this is one that I told you didn't have to memorize. So you may not be able to use pKs to predict this one. But if you were, you would just say the reaction lies to the side opposite the stronger acid, lower pKa, that's the stronger acid, conjugate acid. So the reaction will lie opposite or to the left. Okay, but if you didn't know that, then move your focus away from the acids over to the base and the conjugate base and compare them. Okay, well, if we compare the base versus the conjugate base, on the conjugate base, the negative charge is just stuck on a carbon. There's really nothing stabilizing it. No electronegative atoms, no large atoms, no resonance, nothing. Versus in the base, you can move those electrons toward the carbonyl and get a resonance structure. That is a stabilizing factor. This has resonance stabilization. Okay, the base is more stable than the conjugate base, and the reaction lies toward the more stable thing. So confirming our pKa analysis, the reaction lies to the left side. Okay, is there any other acid-base similar reactions you want me to do? Okay. Uh-huh.
So CH3OH plus NH2.
Okay. And we want to just figure out the products and do the arrows for this one? Okay, so with this one, what you want to do, kind of one of the first highlights that should jump out to you is the NaNH2. Metal cation with nonmetal anion. Okay, this kind of goes back to thinking a little bit about Chem and ionic type compounds. But immediately think of this as Na plus, NH2 minus. And the sodium is just a countercation that we really don't care about. Okay, NH2 minus, if we have a nitrogen with 2 hydrogen, in order to get its octet, you should know that there are 2 lone pairs on the nitrogen. Okay, then if you look at CH3OH, let me just draw it out a little better. Okay, we have to have a hydrogen as the acid. So it could be a hydrogen on the carbon or the hydrogen on the oxygen. Well, thinking about our trends, oxygen is more electronegative than carbon, so hydrogens on oxygens are more acidic. So this is the most acidic hydrogen in the molecule. Okay, so we want to predict the products, and we'll draw the arrows. So we have our acid, our base. Always start your arrow at the base. So I'm going to put my pencil down. I'm going to do it on the lone pair. If you didn't draw the lone pairs and you just used the negative charge, that's fine. Okay, so we'll start there. Draw our arrow to the proton to show that that lone pair is forming the bond. Hydrogen can't have two bonds, so if we put something into it, something has to pop out of it. And these two electrons between the hydrogen and oxygen just move on to the oxygen as a lone pair. So we'll draw the products. Okay, the oxygen already had two lone pairs, now it has three. You can draw all three or just draw the negative charge, either's fine. And then the hydrogen gets bonded to the NH2. Okay, so now we have our conjugate base and our conjugate acid. Okay, if you wonder what happens to the sodium after the reaction, it'll float over and kind of hang out by the O-. Okay, now for this one, this is a good one to predict which way the reaction lies. Even though I drew a solid arrow, you can do the analysis here. Compare the base and the conjugate base. Okay, we are comparing O- and N-. They're in the same row, so it's an electronegativity argument. Oxygen's more electronegative than nitrogen. It better stabilizes the minus. Okay, so the right side is preferred. So if you drew equilibrium reaction arrows, the large arrow would point to the right. Okay, any questions on how we did this one? Okay, other questions? Yes.
So in the nomenclature videos on the problem solving videos, there
Uh-huh.
were some like weird ones where you had like a 3,4, 2-methyl, 1-propoxy, cyclohexane. Do you guys know those?
So this semester we're going about nomenclature in a slightly different order. Last semester we did sort of all the nomenclature up front. This semester we're going to do it functional group by functional group. So right now we've just covered alkanes and haloalkanes. Later we'll do cycloalkanes, and then we'll do ethers, so that's the propoxy and things like that. So no, you're not responsible for the more complex naming at this point. Yes?
Can you explain how you learned orbital a lone pair will reside in?
What orbital a lone pair resides in?
Yeah.
Okay, yes. All right, so the best way to look at this is just through a couple of examples. Okay, so on all of these structures, we have a few lone pairs. And we want to figure out exactly where the lone pairs reside. Okay, so this comes down to knowing a little bit about hybridization. So the first thing you want to be able to do is look at the atom and predict what its hybridization is. So in this first one, nitrogen, we have 4 groups around it. 3 bonds and a lone pair. Four groups is sp3. Okay, but to think more about the orbitals and where the lone pair resides, you need to know a little bit more about sp3 hybridization than just the fact that it's sp3. Okay, when we did hybridization, remember that when we did sp3 hybridization, the net result after hybridization was 4 sp3 orbitals. So that's what we have to work with. Okay, so now going to our molecule, each bond is made from the overlap of orbitals. So this bond to the carbon, even though we don't care so much about the carbon at the moment. Of course, this is the sp3 orbital from the carbon, but that's an entirely different count. Okay, we're looking just at the nitrogen. So this is the nitrogen sp3 orbital forming the first bond. Okay, so that's one. Second sp3 orbital forms the second bond. The third sp3 orbital to form the third bond. Okay, the only orbital we have left is an sp3, so that must be where the lone pair is. So that's our only option there. Okay? So now let's look at the second one. So the oxygen, its hybridization, you should know, is sp2. There's one bond, the double bond, and 2 lone pairs. Okay, sp2, remember when you start out with the s and 3p orbitals and hybridize them, for sp2 we actually hold 1 p orbital back. So we keep a p and we get three sp2 orbitals. Okay, so we can figure out where each orbital is involved. Okay, so with the oxygen, the single bond, or the first bond between the oxygen and carbon uses an sp2 orbital. Okay, sigma bonds like hybridized orbitals. So there we've used one. Okay, but the pi bond, so the second bond between the oxygen and carbon, it's getting a little messy, but the pi bond uses the p orbital. Okay, so all we have left are 2 sp2s. So that's where the 2 lone pairs must reside. Okay, then finally, in the third example, we're looking at this carbon. There's a triple bond and a lone pair, 2 groups, sp hybridized. You want to know the 4 orbitals you have to work with sp. You have 2 p orbitals held back and 2 sp orbitals. So the first bond between the 2 carbons uses an sp orbital. Then we have 2 pi bonds, each require a p orbital from the carbon. So that uses our 2 p orbitals. Now all that's left is an sp orbital to put the lone pair in. Okay, does that make sense? Yes?
Are there going to be a situation when it's not the same
The question is there going to be a situation where it's not the same? The answer is yes, but we haven't gotten there yet. So for this exam, there won't be a situation where it's not the same. Okay? Yes?
On the exam for the bonus question on the practice one, it's like the methyl cation H3C+. Could you go over that?
Yeah. Okay, so we're going to look at the bonus question number 25 on the practice exam. Okay, and really using the stuff we've talked about, this isn't a hard question. So I said the methyl cation CH3+. Okay, how many groups are around that carbon? We have 3 bonds, no lone pairs. Positive charge doesn't count as a group. The positive charge is a whole. Three groups. sp2 hybridization. Okay, and you want to know, as soon as you see sp2, what 4 orbitals you have. You have 1 p that is held back from hybridization. And 3 sp2 orbitals. They all look kind of like this. Okay, so that is for the carbon. Okay, the hydrogens are easy. Hydrogens are always just s orbitals. Okay, so we want to draw the picture to show what's going on here. So I have my carbon. Okay, sigma bonds use the hybrid orbitals on carbon. Double bonds, triple bonds use p orbitals. Okay, so we need 3 single bonds or sigma bonds to the hydrogens. We're going to use these 3 sp2 orbitals. Okay, and let's arrange those around as far apart around the carbon as possible. So there's carbon's sp2, sp2, sp2. Okay, but we know the carbon also has a p orbital, and it has to be there. So let's go ahead and draw it on. Okay, so we got all the orbitals on the carbon. Okay, now let's put the hydrogen around it. And the hydrogen, we're going to use s orbitals, and we're going to attach those to the sp2 orbitals to form the sigma bonds. Okay, we've taken care of all of our atoms, and essentially we are done. Okay, what happens is we end up with sort of this unused or empty p orbital. Okay, now the plus is really just a formal charge. You don't have to draw that in because as soon as you see this p orbital with nothing bonded, that tells you it's the positive charge. But I went ahead and drew the plus in the p orbital just to show kind of where it's sat. Okay, other questions?
Can you review third degree and second degree functional groups? Like number 13 in practice?
Oh, okay. Yes. All right, so functional group and labeling them based on the carbons. So I will go ahead and tell you, so we're looking at number 13 on the practice exam. Amines are kind of different. We haven't covered amines yet. Don't worry about amines, okay? Okay, but the others are pretty easy to figure out. So instead of actually going through number 13, let's just look at a couple of examples. Hey, Blake.
What are you doing, man?
Hanging out, having a review.
So am I. I should reserve this from 4 to 6.
I reserved it.
I reserved it.
Are you sure?
Yeah, I talked with Becky about it. How long are you holding your review session?
4:30. It's over.
Okay.
Now I'm curious. I want to look.
It's all right. This is awkward.
Yeah, a little bit. And we want to figure out exactly what they are: primary, secondary, tertiary, or quaternary. Okay, now just the basic carbons are pretty easy. So look at the carbon that I've highlighted, and it'll be the same way on the test. And all you want to do is essentially figure out how many other carbons are attached. So this first one with the red arrow, we're looking at this carbon. Attached to it are 2 other carbons, so that's secondary. Okay, if you want to look at this one, okay, look at how many carbons are attached to it. There's 4 carbons directly attached. That's quaternary or 4'. Okay, now if you're dealing with, we started talking about functional groups. Okay, it's really nothing new. Okay, we'll classify this as, you might call it a chloride instead of a carbon, but look at the carbon. Okay, how many carbons are attached to that? 2. Okay, don't let the chlorine throw you off. Okay, you could still just call that a secondary carbon, or a better name for this, now that we know functional groups, a secondary chloride. Okay, do the same thing with an alcohol functional group. Okay, look there. Just look at how many carbons are attached. 1 carbon attached. That's a secondary functional group, is an alcohol. Okay, or you could be asked about hydrogens. Okay, you have your carb. Yes?
Why is it secondary?
I don't know. Because I'm tired, I guess. Sorry. We'll black that out. It's attached to 1. 1 is a primary alcohol. Good spot. Okay, and then the last one, we're just looking at the hydrogen. So we have 2 carbons attached, So this is a secondary carbon. And you can also say that these are secondary hydrogen. Yes?
For the secondary chloride, would you like, would it counted right on a test if you called it like a secondary halide?
Yeah, that's fine. Secondary halide. Okay, other questions? Okay.
This one right here.
Okay.
This is the answer.
To name it?
Yeah.
All right, so we'll do that. All right, so it's a naming question. Okay, we want to figure out the IUPAC name for this. So let's first find our longest continuous carbon chain, which I think is pretty straightforward. Let's see. Go with that. Lighten it up a little. Okay, so there's our longest carbon chain. Right, I think probably the confusion comes with maybe numbering it. So we have two options on numbering. So I'll do a red numbering scheme. Oops, a little big. Number 1 through 7, or a blue numbering scheme. Okay, so a common misconception is for people to say, oh, well, halogen must be more important, so let's give it the priority. You do not care at all about the identity of the group ever. Okay, so your first goal is lowest numbering. Only when you come to an unbreakable tie, then you go to alphabetical priority, but not identity. Okay, so in this case, the red numbering scheme, well, in both cases, are substituent at carbon 2. Okay, and honestly, based on the number of questions I've gotten about this, I probably didn't make this clear enough in class. But if we compare the two schemes, it's better to have two things at 2 versus only one. So that's why the red numbering scheme is the better.
So you go by the number of substituents, but if they were both had 1, then you would do like the alphabetical name, right?
Yes. So if you just had 1 like this, in both cases you would get a tie. Your second substituent falls on carbon 4 in each. So we use alphabetical priority. And the B gets priority, so we would number from right to left. Okay, and I'll just quickly get the name of this one. We have 6-bromo. Then on carbon 4, I think it's easiest to call that a tert butyl. Okay, if you want, you could name this as a complex substituent, which would be, you would number 1 and 2, so you would do 1,1-dimethyl ethyl. And then on carbon 2, we have 2 methyls. Okay, so let's alphabetize these. The bromo comes first. Yes. So you will have to specify where it is on the parent. So we do our 6-bromo. I'm going to use the tert butyl, so we'll use the B alphabetically. So we have the 4-tert butyl. I'm going to combine the methyls and do 2,2-dimethyl. And 7 carbons is heptane.
You abbreviated T-butyl?
Yes, you can write T-butyl instead of tert butyl if you want. Other questions? Yes.
Can you go over an example of recipe?
With a negative charge or positive charge? Negative charge. All right, resonance. So, let's do one with both maybe. We'll see how hard we can make it. Let's say we want to draw the resonance structures for this molecule. So what we can do is you want to start and focus in on a charge. Okay, this one you have a negative and a positive. It doesn't matter which side you start at. Okay, I'm going to start at the negative. Okay. So what you want to do is identify 2 or 3 atom systems. I want to make it a little harder. Oh shit. Oops. All right, now we can go on. All right, so identify 2 or 3 atom systems where you can move electrons. We're going to focus in on the negative charge. Okay, and only look at that small grouping of atoms at a time. Okay, so we're going to look here. We're going to start by, always put your pencil down on the electrons you have. So I'm going to put my pencil down here on the negative charge, which is, there's a lone pair there. I'm going to push those electrons down to form a double bond between the oxygen and carbon. But this carbon can't accept any more bonds without giving something up. So what's going to happen, this pi bond will move on to its neighbor as a lone pair. And that's how we get the first resonance structure. There's our double bond to O. And we put a lone pair here, or you could have just written it as a negative charge. Okay, there's no reason to look backwards. Just like life, you always want to look forward. So go with the next 3 atoms in the system. Focus in on them. See how we can move the electrons. So I'll put my pencil down on the lone pair. Move this in to form a double bond here. Again, the carbon can't accept extra electrons without pushing some away. So now I'll push this pi bond as a lone pair onto its neighbor. Okay, it's sort of like a tandem. Keep pushing in the same direction. Okay, so now we got another resonance structure. The other thing is only make changes at these 3 atoms. Okay, that's where you're doing movements. Everything else, leave alone. We haven't, from this structure to the next, we haven't changed this double bond to oxygen, so don't screw with it. Okay, so leave it alone. Okay, so we get this compound. Now looking forward to the next set of 3 atoms. Okay, we have them next to a double bond. Okay, now a question I sometimes get is, why can't we do, get another collar. Why can't I move them up here? Okay, the problem is we have 2 hydrogen there. That's going to give a 5th bond to carbon, and there's no double bond up there to move away. So you can't do that. Okay, so we're only moving them where we can do valid movements without going over our octet. So let's move these down. That'll pop this double bond over onto that carbon. So we have the lone pair and the minus there. Okay, and now we can look ahead. We have another 3 atom system. Well, I didn't mean to circle the carbon and hydrogen there, but we really care about the carbon with the negative, the carbon with the double bond, and the oxygen. So I'll push those electrons down to form a double bond. Push those up onto the oxygen. The oxygen's positively charged, so it's more than happy to take those electrons. Okay, and if you want, you can even draw those electrons we pushed onto the oxygen ends up being its second lone pair. It already had one. Okay, now this is one, I'm not going to walk through all of this. This is one I would encourage you to come back to and now start on the other end, start down at the OCH3+. Start with this 2 atom system. Move the electrons to the oxygen, which will give you a carbocation here, and push your way around and draw the resonance structures going in that direction. Okay, any questions on this one? Yes? Could be both. So multiple choice, sometimes I'll just put something that's like which structures represents resonance structures, which is fairly easy. On the test, I'll go ahead and promise you that there is a section very similar to question 19 on the practice exam where you're given resonance structures. I will give you resonance arrows to kind of indicate how many you need to draw. Okay, and you'll draw out the resonance structures and use arrows to show your electron flow. Yes?
Is there a way to know how many resonance structures you're supposed to have with something, or do you just have to like go through all of that and make sure you
So the question is there a way to know how many resonance structures? And the answer is no. You can only start drawing and see how many you end up with by the time you're done. It's kind of like trying to draw isomers. You don't know how many you can get until you start drawing and run out of possibilities. But for the exam, like I said, I direct you as to how many you should have, so it makes it a little easier. Other questions? Yep.
So which one's more stable? The last one?
Yes, so the last one by a landslide is more stable because there's no charges, so we've minimized charges. So this would be the best, the most stable, or the major contributor, however you want to say it. Okay, and just to kind of reiterate, these aren't individual structures. The true structure is a resonance hybrid. This is just our attempt to show where the electrons are localized at through the molecule. Other questions? Yeah. Yeah, isomers aren't my favorites, but I'll do one. Okay, and I'm not going to promise I'm going to find all the isomers to this one, but we'll do our best to get as many as we can. So let's say I want the isomers of C3H6O. Okay, it doesn't matter how you connect your atoms, as long as you get them all in, they all have their octets and their valid structures. So we could do CH3. Well, this one, so I'm going to run into a problem you might run into and show you how to fix it. So let's say you try to put your carbons in a row. So there's your 3 carbons. Maybe you want to put an oxygen in, like an OH, and we end up with 8 hydrogen. Okay, so we clearly use too many hydrogen. When you don't have enough hydrogen to work with, that's when you want to start thinking about double bonds, triple bonds, or rings. Okay, so in this case, the easiest thing to do would just be, let's knock a hydrogen off each of 2 adjacent carbons. Oops. Do CH. And we'll get this. Okay, once you get one valid structure, it becomes easier to work with. So let's draw this as a zigzag. Okay, then just think about ways you could move atoms around to still keep a valid molecule. You can move the double bond, and you'll still have the same atom count. If you don't believe me, go through, draw them in, and count them up. Put the double bond on the oxygen. What else could we do? Let's take this one, and I'm going to rip the methyl group off the end and move it over closer to the OH. So that's an isomer. We can move the double bond to there from that isomer and get another. Another good option, with hydrogen counts, rings and double bonds are kind of equivalent. They both end up with a subtraction of 2 hydrogen. So you could have come up with this. This still has your 3 carbons, 6 hydrogen, and an oxygen. Could have done a 3-membered ring with an OH on it. I'll do one more. I'll put the O between the double bond, like this, between 2 carbons, to make an ether. Okay, so those are all isomers. They all look very different. They're different molecules, but they have the same formula. Okay? All right, so I guess we better wrap up here so the Chem 115 class can have their review.